So everybody has a partner, right? I think that's right, yeah. I think I talked to all of you. Okay. Yeah. She told me. Does it, oh? You don't actually like it, do you? I don't like it much.
Who made it for you?
They made it for me. So
Sorry. That's pretty amazing.
I got the answer in the same mug. Probably have one like this too, right? That's true.
Yeah. Everybody is there for a semester.
And it's kind of sad because I need to say this quick before I start getting recorded. So someone hand makes them for you, and it's just some staff member at MSRI, and I don't particularly like the mug, but somebody went through the trouble of putting my name on it even. They even ask you what you want written on there, so you could even get clever and write something different. Yeah, it feels good to drink from, I think, but I don't know. Well, you can't just give it away because it's obvious whose it is, especially. No, I mean, if your name is Jim Smith, maybe you can do it, but with my name and with MSRI on the other side.
By the way, it's already started.
It did? Are you serious?
Yeah, it's 2:13. When you were out of the room, it said it started.
Are you kidding? Oh, that's terrible. Okay, so I'm not gonna post the lecture today then.
We're gonna shoot it over to MSRI.
How could you not tell me? Man. Okay. So yeah. In the last two classes, we talked about the volume of the permutohedron, and we saw that it's beautiful. The volume is n to the n minus 2, and we have to use ideas from several different parts. And what I want to do today is do a similar example with a different polytope. Something called the Pittman-Stanley Polytope. Okay, so the Pittman-Stanley Polytope, and I don't know if it has this name, but I'm giving it this name. PS sub n is the set of vectors y in R to the n such that all the y's are greater than or equal to 0, and the sum of the first I variables is greater than or equal to I. So this is for all I. This is for all I. And the sum of the variables is n. Okay? And again, with this business, it's hard to draw very many examples, so I'm going to draw PS3. Okay? So my coordinates are non-negative, and that means that I'm on the positive orthant. Y1 plus Y2 plus Y3 equals 3, and so this is the plane x plus y plus z equals 3. And now I need to put in these inequalities. So the first inequality says that y1 is greater than or equal to 1. Okay. Now if you see 1 is this height, and so y1 goes from 0 to 3, and so what I need to do is cut it into 3 parts. So here, y1 is 0, y1 is 1, y1 is 2, and y1 is 3. Okay, the same thing here. And so that means that the first inequality tells me that I need to be over here. y1 should be bigger than or equal to 0. Okay. By the way, I should be drawing a plane, but because my polytope is on on this plane, then I'm just going to see how the coordinates cut, how these inequalities cut the triangle. Okay. So y1 is bigger than or equal to 1, and then y1 plus y2 is bigger than or equal to 2. Okay. Now, you see, because the sum of the variables is 3, that means that it's a little bit easier to write this as y3 less than or equal to 1. So that means that now y3 is the height here, so I should draw here y3 is equal to 0, 1, 2, and 3, so this is where y3 is less than or equal to 1, or in other words, y1 plus y2 greater than or equal to 2. Okay? And so that means that, and the variables need to be greater than or equal to 0, so that means that this is the Pittman-Stanley Polytope. Okay? That's what it looks like. Okay. So what I want to do is compute the volume of this polytope, and my technique is going to be similar to what I did last time. So first, what I'm going to do is express this polytope as a Minkowski sum of simple things. And it's going to look like this. So here, when I write delta sub 1, 2, up to I, what I mean is the simplex with vertices E1, E2, up to EI. Okay? And as you know, this is given by the inequalities. First, the sum of the coordinates should be equal to I, and the coordinates should be non-negative. Okay, so that's the convex hull of E1 up to EI. And because my vector is in Rn, that means that it has additional coordinates xi plus 1 up to xn, and those should be all equal to 0, right?
I think the coordinates just sum to 1.
To 1, thank you. Yeah. Yeah, the sum of the coordinates is 1. So that's the standard simplex, right? So for example, what am I saying for n equals 3? I'm saying that the Pittman-Stanley Polytope 3 is equal to delta 1 is the convex hull of E1. Okay, so that's just a point, E1. Then delta 1, 2 is the segment between E1 and E2. And then delta 1, 2, 3 is the triangle E1, E2, E3. Okay? And a segment plus a triangle looks like you take the segment and you move it around the triangle, and you see that what you get is this. And then when you do the Minkowski sum with E1, that just shifts you a little bit. Okay? But so what we get is exactly this polytope. That's what I'm going to prove. Okay? Well, I'm going to give you a sketch of the proof. So what I'm going to do is prove one direction and then leave the other one for you as an exercise. So what you should do is the following. Let's notice that in delta 1, we have that this only has one point, which is the point that has first coordinate 1 and the other coordinate 0. So that means that y1, being the first coordinate, is greater than or equal to 1. And y1 plus y2 is greater than or equal to 1. y1 plus y2 plus y3 is greater than or equal to 1. All of these inequalities are satisfied because y1 is bigger than or equal to 1, and then everything else is greater than or equal to 0. Right? Now let's look at delta 1, 2. Okay, so this is the convex hull of E1 and E2. And so here, by the way, I think actually I should be more precise than this, because y1 is actually equal to 1. So there's no point in writing greater than or equal, because this is an equality, right? y1 is equal to 1. And y1 plus y2 is also equal to 1. And all of these are equal to 1. Because, like I said, y1 is 1 and the other y's are 0, because this is just the point E1. Okay? In delta 1, 2, this is the convex hull of E1 and E2. So we know that y1 plus y2 is equal to 1. And then all the other coordinates, here you don't see any 3s or any 4s and so on. So all the other coordinates are 0s, and so you have all these equalities. Okay? But what I cannot say anymore is that y1 is equal to 1, because, in fact, in this segment between 1 and 2, y1 could be anything between 0 and 1. So that means that all I can say is that y1 is bigger than or equal to 0. That's all I'm going to say. Okay? Let's go to the next one. Okay? So in the convex hull of 1, 2, and 3, I know that y1 plus y2 plus y3 is equal to 1. And everything after that, all of these guys are equal to 1. Okay? What I don't know is what these are equal to, and all I can say is that y1 is bigger than or equal to 0, and y1 plus y2 is greater than or equal to 0. Okay? So you see, what I'm doing is that in each one of these simplices, I'm just finding out what I can say about these values. Okay? And I'm doing it for each one of these things until the last one, where I know that the sum of the coordinates is 1, but then for everything else, I don't really know anything, except for that y1 bigger than or equal to 0, y1 plus y2 bigger than or equal to 0, y1 plus y2 plus y3 bigger than or equal to 0, and so on. Okay? The point is that then, if I do the Minkowski sum of all of these polytopes, so in other words, in the right-hand side polytope, what's going to happen? Well, what you're going to get is that a point in the Minkowski sum is given by taking a point in here, a point in here, a point in here, a point in here, and adding them. Okay? And so that means that y1 is going to be greater than or equal to 1 plus 0 plus 0 plus 0, etc. y1 plus y2 is going to be bigger than or equal to 1 plus a bunch of zeros. y1 plus y2 plus y3 is bigger than or equal to 1 plus 1 plus 1 plus zeros, so on. And then here, you get an equality, and you get n. Okay? So that means that what I showed is that every point in the right-hand side satisfies all the inequalities of the Pittman-Stanley Polytope, and therefore this right-hand side polytope is contained in the Pittman-Stanley Polytope. And so that at least makes this plausible. And for the other containment, I'm going to leave it as an exercise, but the point is basically that you're not going to get any new inequality directions. These are going to be the only ones that appear. Okay? So that's the lemma. Okay? That's the nice expression of the Pittman-Stanley Polytope as a sum of simple things. All right? Any questions so far? Okay. So a corollary of this lemma is that we're going to be able to get a formula for the, maybe not exactly a formula, but at least an expression for the volume of the Pittman-Stanley Polytope. Okay? Because it's going to be just as we said last time, a sum of mixed volumes. Right? Now, let me write this in shorthand. This is going to be delta of in square brackets 1, delta in square brackets 2, up to delta in square brackets n. Okay? And so we know that if I want the volume of a Minkowski sum, what I have to do is take all the mixed volumes of the polytopes n minus 1 at a time. And why n minus 1 at a time? Because this is an n minus 1 dimensional polytope, right? It lives in n dimensions, but it lives on a hyperplane. Okay. So what I have to do is that I have to add up all the mixed volumes of all the things of the form delta I1 up to delta I n minus 1. And I have to do this overall I1 up to I n minus 1. Okay? So that's an immediate corollary by all of these. I mean, we did the same thing with the Bermuda-hedron. Now we do it for this guy. And remember then what we did for the Bermuda-hedron was that we found a nice expression for this by translating it into Bernstein's theorem. And so that's the plan here also. Okay? So this is what I want to compute. Okay? And to do that, I need a lemma. So, or rather a definition. I'm going to define a reverse parking function. A reverse parking function A1 up to AN is an n-tuple of integers between 1 and n having at most I elements which are less than or equal to I. Okay, and I'll explain later why I'm calling it a reverse parking function. But for now, let's just make sure that we understand what this definition is saying. So for example, for n equals 3, what do these things look like? We're basically saying you have at most one element which is less than or equal to 1. Okay? Now, if you're less than or equal to 1, you have to be 1, because these are positive integers. So that means you have at most 1, 1. Then you have at most 2 numbers that are 1 or 2, and then you have at most 3 numbers that are 1, 2, or 3. Okay? So the numbers could be 1, 2, and 3, for example. That's fine. And you can reorder them in any way, and this doesn't care about order, right? So you could go into 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And these form kind of a first bundle of parking functions. Now, what else could we do? Well, you can have... You basically are able to be bigger than this. This is kind of the smallest parking function because it has 1 number less than or equal to 1, 2 numbers less than or equal to 2, and 3 numbers less than or equal to 3. And you can increase things a little bit. For example, you can have 1, 3, and 3, and that's fine. Right? It still satisfies the conditions, and then you can reorder. So 1, 3, and 3, 3, 1, and 3, 3, 3, and 1. Okay. Do you guys see any other parking functions? Can you think of any? For example, 1, 2, 2. Does that work? That doesn't work because it has 3 numbers less than or equal to 2. Right? 2, 2, 3 works. 2, 2, 3. Again, remember the point is you want to be kind of bigger than this thing. 2, 2, 3, and we can permute it. 2, 3, 2, 3, 2, 2. Okay. Can you think of any other ones? Which one? 3, 3, 3. And you can't really permute that one, so that's going to have to be alone. Can you think of any other ones? 2, 3, 3. 2, 3, 3. 3, 2, 3, and 3, 3, 2. And if you think about it, that's it. Okay. It really kind of takes trying all the possibilities and figuring out that these are all of them. Okay. So those are the parking functions. Why am I defining them? Well, for the following reason, lemma, the volume of delta I1 up to delta IN minus 1 is going to be 1 over n minus 1 factorial if I1 minus 1 up to IN minus 1. Minus 1 is a parking function, or a reverse parking function. And it's going to be 0 otherwise. Okay. So that's why I define them, because they're exactly what comes out when I try to compute these volumes. You get basically a 1 if you're a parking function and a 0 if you're not. Okay. Proof. Well, we know that we're basically counting solutions to a system of equations. Okay. Now, let's write these numbers in order as J1 less than or equal to J2 less than or equal to less than or equal to Jn minus 1. Okay? And I think, let's see. I mean, what do these systems look like? The system is going to look like this. So we're counting solutions, well, isolated solutions with no zeros to a system of equations. Okay? And the system of equations looks like, I'm just trying to think of, I think it's better if I just do it in an example. So let's take an example for n equals 5. Okay, so can you guys tell me a parking function for n equals 5, a reverse parking function? Maybe not the most trivial one, but something a little bit more interesting. Oh, so okay, so what's the most trivial one, first of all? It's 1, 2, 3, 4, 5. Okay, so how do we make it less trivial? Kind of, or it could be 5, 5, 5, 5, 5. Maybe that's the most trivial one. So something in between. So tell me something in between. That's sounding a little too trivial. Less trivial. It's kind of something in between, right? So maybe 2. What's the first number? 1. Tia, give me another number. 3. Michael. Now you guys actually have some responsibility. Don't be too carefree here. Dito. We can't choose 2, right? Why can't we choose 2 if we want to be a reverse parking function? Because then we would have 4 numbers less than or equal to 3. So maybe 4. What about you, Abraham? It has to be 5. It can't be anything else. But so this turned out to be a little too trivial. So how can I make it less trivial? I can say, for example, let's take this 1 and make it a 2. Let's make this guy into a 5. Okay. So this thing has at most 1, 1, at most 2 1s and 2s, at most 3 1s, 2s and 3s, and so on. This one is fine. Okay. So what is the system corresponding to this? Well, it's delta. So we're looking at volume of delta 2, delta 3, and so on. Okay. So delta 2 has support 1 and 2. Right? These are the 2 variables. So something x1 plus something x2 equals 0. Delta 3 has something x1 plus something x2 plus something x3 equals 0. Okay. Delta 5 has something x1 plus something x2 plus something x3 plus something x4 plus something x5 equals 0. Okay. 4, something x1 plus something x2, this. Okay. And then 5 looks like this. Okay. There's something that I don't like about this.
So when we're saying they're generic, right, the third equation and the last equation aren't going to necessarily have the same coefficients, right?
Right, so as part of the assumption of being generic, these stars are different from these stars. So they're not going to be the same equation. Okay. But there's something else that I don't like about this, which is that, what is it? I'm having a trouble with n. I need your help because the thing is that here I used parking functions with n, and here I use them with n minus 1. Okay? If you see here, what I have is a parking function of length n minus 1. Okay? So really, let's say that n is equal to 6. Okay? And now I am doing, this is a parking function of length 5. Okay. But you see the parking function has 1 subtracted to it. That's the other thing that's confusing me. So really, this is the volume of delta 3, delta 4, delta 6, delta 5, delta 6. Yeah? I'm saying that the volume of delta I1 up to In minus 1 is corresponding to subtracting 1 and seeing if that's a parking function. Okay? So that's why I'm confused. And so that means that I need to make these equations all 1 longer. Okay? And let me just, instead of putting it to the right, let me just add a variable to the left. Okay. Okay, now I like this better. I like this better because we're supposed to have a problem here, which is the same problem that we had last time, that this is not supposed to give us the right answer because we are not in the right dimension. Right? Remember that we're doing an n minus 1 dimensional volume, and so just as last time, here we're trying to count solutions of a system that is overdetermined, or underdetermined rather. You have 5 equations, 6 variables. And we saw that what you had to do last time was set one of the coordinates equal to 1. Okay? So, and that's really going to be the correct counting problem. So I'm not going to go through the argument again. I said it last time, but remember what we did last time was take one of the variables and send it to the other side. Okay? And that's what I'm going to do here. Instead of having these guys, what I need to do is put generic numbers here. And that's really the system of equations that I'm trying to solve. Okay? This is the system of equations that I'm trying to solve. Okay? And let me write it in matrix form. So what does the matrix look like? It's some matrix like this. Times x1, x2, x3, x4, x5 equals stars. Okay? And we need to count the solutions to this system of equations. Okay? Now, these were my i's, right? I1, I2, and so on. And remember what the j's are subtracting 1 from them, so the j's are these numbers, except that they are ordered. The j's are ordered in increasing order. Okay? So this is j1, j2, and so on, but I put them in increasing order. Okay? And the way that I do that here, so what I'm saying basically is that here I have j1 things, here I have j2 things, but to get these numbers in increasing order, what I'm going to do is just flip these two so that this is a nice staircase shape. That's what it means to have the j's in order, that I I can swap rows in the system of equations so that it has a staircase shape. So I'm gonna swap these two rows. Okay. Now, really, what I should be doing is erasing these 4 numbers, erasing these 5 numbers, and then kind of writing everything again. Right? It's not done that I'm taking this number and moving it over. It's just that the stars represent actual numbers, right? But I swap the rows, and now it looks like this. And now, this is J3, this is J4, this is J5. Okay? Now, let's observe something. This is a parking function if and only if what? I can have at most one of these numbers equal to 1. Okay? At most 2 less than or equal to 2. At most 3 less than or equal to 3. And so on. So really what that is saying is that I have to stay above this diagonal, right? If for example, or sorry, I drew it wrong. So what this is saying is basically that J1 has to be bigger than or equal to 1, J2 has to be bigger than or equal to 2, Jn minus 1 has to be bigger than or equal to n minus 1. For example, if J2 was not less than or equal to 2, then it would be less than or equal to 1. But it's the second largest, and that means that there's 2 numbers less than 1. Okay? So the point is basically that I have to have asterisks in this position, in these positions. Okay? So if this is a parking function, then I get to hit those asterisks. If it's not a parking function, then I miss them. Okay? Now, if you think about what that means, for example, what happens if I miss this asterisk right here? That means that this is going to be a matrix with determinant 0. Right? I mean, this thing is in staircase shape, okay? And so if I miss one of these asterisks, that means that the determinant is going to be 0. And if I don't miss any of them, that means that the determinant is not going to be 0 because these numbers are generic. Okay? So this is true if and only if, when I write this matrix A, the determinant of A is not 0. Okay? Now, what happens? If the determinant of A is 0, that means that this is a system of equations that is dependent, and that means that it has infinitely many solutions, or no solutions, but it doesn't have a unique solution. Okay? So, if the determinant of A is 0, then I don't have exactly one solution because the matrix is not invertible. Okay, so and that means that my volume is 0. Whereas, if the determinant of A is not 0, then this matrix is invertible, and that means that there is a unique solution. Exactly one solution. Okay? And I also claim that that solution has no 0 coordinates. Okay? And let me just argue quickly why that is. Because for example, how do you solve for x4? Let's argue that x4 is not 0. Okay. Well, what is x4? Well, if you remember what Cramer's rule says, Cramer's rule tells you that x4 is, in the bottom you get the determinant of a, and in the top you get the determinant of a4, where a4 is obtained by taking the fourth column and replacing it with this. That's what Cramer's rule says. Okay? So I'm taking this column and putting it into here. Okay? And so what I'm doing effectively is put in more non-zero entries. Okay? And again, because my choices of numbers is generic, that's going to mean that when I do that, this is going to be non-zero as well. Okay? This is not 0, and this is not 0. Okay? And so that means that I have exactly one solution, and that solution is in c minus 0 to the n. Okay? And so that means that if I do have a reverse parking function, then n minus 1 factorial times the volume, which is the number of solutions of the system of equations, is exactly 1. And that's what I wanted. Okay? So that proves my lemma. Okay. I think I want to make one more comment about this proof, because it's something that I think is interesting both historically and mathematically. If you see the two results that we have proved, we have this result, and last time, if you remember, what we did is that we computed the volume, the mixed volume of taking something like delta of I1 and J1, delta of I2 and J2, and delta of In minus 1 and Jn minus 1. So this is the one that we did last time, and we found that this is 1 over n minus 1 factorial if you have a spanning tree and 0 otherwise. We showed this last time. Now, there's a more general statement of which these two are special cases. And I think that kind of makes sense looking at it, right? And maybe I'll just give you what the idea of what this kind of looks like. You can compute the volume of the mixed volume of any n minus 1 things that look like this. So So of course, these two are meant to be special cases of this, but the point is that you can do this for any sets A1, A2, up to AN minus 1, where delta of a set is the convex hull of the basis elements in that set. Okay? And again, you're going to get something like this. Okay. So when is it that you get 1 over n minus 1 factorial, and when is it that you get 0? You can basically run through the same proof that I just said, and let me just tell you what you're going to get. It's very interesting. So these sets have to satisfy the dragon marriage condition. You know this is going to be good. The dragon marriage condition. Okay? And so we have marriage and we have a dragon. So this is going to be like our dating agency problem, except that there's a dragon involved. Okay? And it looks like this. Let's say, for example, that n is, I don't know, 4. And so you take 4 sets. Okay? And they should be subsets of the numbers from 1 up to n. So again, I'm going to make you guys tell me what the sets are. So who didn't I ask last time? 2, I didn't ask you last time. So tell me a subset of 1 up to 4.
A subset?
Any subset.
1, 2.
1, 2. Rika. 3, 4. Jimmy. 2, 3. And I think Tristram is the last one. 1, 2, 4. Okay. So this is gonna. Oh no, but no. Sorry, Tristram, you don't get to participate. You don't get to participate because I was only supposed to do n minus 1. Now let's let him participate. N equals 5. Okay. And that means that you could have put 5s in there. So let's throw in some 5s for good measure. So I get to choose where I put the 5s. Okay. So these are 4 subsets of the numbers from 1 up to 5. And now we're going to treat these as marriage preferences. So as before, so here what I'm saying is that 1 could be married to 1 or 2. 2 could be married to 3, 4, or 5. 3 could be married to 2 or 3. And 4 could be married to 1, 2, 4, or 5. Okay? Now you see there's a problem because there's too many women. So these are men, and these are women. Okay? But then there's a dragon also. And the dragon gets to come in and just rob one of the women away. Whichever one the dragon wants. Okay? And then you are then supposed to find a matching no matter which woman the dragon took away. Okay? If that's possible, then this set satisfies the dragon marriage condition. And if that's not possible, then they don't. Okay? So for example, let's say that the dragon comes and takes 2. Okay, so the dragon comes, says, I'm taking away the second woman. Okay? Can you match the remaining in pairs? You can. You can match 1 and 1, I just did it. What happened? 3 and 3, 2 and 4, and 4 and 5. Okay. So if the dragon takes away woman 2, everybody else can be matched. Okay. But you're supposed to check that for every single woman. Okay. And if that holds, then we say that these guys satisfy the dragon marriage condition. And that's, I mean, this is just what comes out of the mathematics. You're really trying to compute a mixed volume. You solve a system of equations, and then this is just what comes out. It is what comes out. And again, the proof is essentially the argument that I just made, but a little bit more general. But the proof is not much more complicated. I think it's pretty cool. Now, the other thing that's interesting about this, so Poznikov did this a year or two ago, but it turns out actually that this had been done by game theorists already. And they were trying to compute the number of mixed Nash equilibria of a system, and then they found that they needed to solve this problem. So the number of mixed Nash equilibria of a certain system is equal to the mixed volume of this. And then they just needed to do this, and then they figured out the answer, and they didn't phrase it in terms of dragons, but anyway, so that's an interesting historical fact. Now going back to this, where we were, what we get basically is that this is 1 over n minus 1 factorial times the number of reverse